Hello, everyone. This is Management of Operations, BUSN 6630, Spring 2021. The lecture this evening, I'll be going over the Quiz 2, Homework 2, and Memo 1. If I get done early, which I hope I do, I will probably go into a little bit beyond the course, things that I like for people to have exposure to. In forecasting, and then move on. Since Quiz 2 and Homework 2 is in optimization, Memo 1 is forecasting. Once I get done with all the assignments, then I go a little bit beyond this course a little bit, if I have time. And I hope so, because it's good material. It's stuff that can be used very effectively in business. Okay, people are starting to show up. And I see I have, it just keeps growing, which is nice to see. And before I get going, I want to say as introduction, the chat room is always welcome. And the questions are good. And as I work through the problems, the Quiz 2, that represents mechanics. Homework is applications. You've probably already seen that. And the Memo 1 is communication. And so if I'm working with Quiz 2 with the mechanics, and a question on application comes up, I might wait until I get to the homework. But if I don't answer a question satisfactorily, then ask it again. And so sometimes when there's a lot of questions here, sometimes I miss them. So just keep asking, and I'll see it. Oh, okay, that type of thing. Okay, before we get to the quiz, let's bring up Canvas. And here's Canvas in the home page, and we are down here on linear programming optimization. Let's open up weeks 4 and 5. And then so notice what I have is homework 1 and memo 1 is due this week by February 14th. Let's see, what do I have here? The memo 1 and quiz 2, no, this is already done. I get things all over the place. Anyway, this is open now. But anyway, linear programming, if you open linear programming, open that module. There it is. And so notice what I did here. I have the lecture of the Word file. And this is what I'm going to cover. That's what I covered last time. But then I have some live streams here, LP Part 1, LP Part 2. And then today, and I did this last time too, I have 2 of them. If you remember, I got some snafus in the links, so I had to do it in 2 parts. And thank you. I really appreciate everyone sticking with me last week too. Tonight, I'm going to just look. This video will be posted here as soon as I'm done. I'll post this here, and you'll have this in video. The Quiz 2, Homework 2, and Memo 1. So I'll be going through these. Okay. And now notice these are Word files. Word files, and Word files. And there they are, Quiz 2, Homework 2, and Memo 2. Memo 2 here so these are everything for linear programming. Okay. Okay, so let's download Quiz 2, Homework 2, and then Memo 1 was from last week. So let's start with Quiz 2. A lot of people have arrived, and the number of arrivals is starting to slow down. So it's been a few minutes, 5 minutes or so. So let's bring up Quiz 2, Mechanics of Optimization. Okay, here we go. And hopefully from the lecture, there shouldn't be that many problems with this, but if there are, you can certainly ask them. Yes, we will do Memo 1 today. Okay, and so these are the application videos, but also they talk about the material. Okay. Now, first of all, I start with just the definition of the problem. Now, remember there are 3 stages: definition, formulation, and solution. And this one, what statement correctly states the business question? And so I have 3 business questions here. And what's important is, what do you want to know from the definition of the problem? And so to define the problem, you say, okay, if I answer that question, do I have everything I need? Okay, and so how much wood do you use? I use this much wood. Well, that's not enough information to know how many tables and chairs do you make, and how much money you're going to make. And so the business question, which is stated in the lecture, I'm just linking that up with the lecture. And then I get to the in the formulation stage. In the formulation stage, which should come first? And I made a point of this, and it's very important what comes first in the formulation stage. And mistakes that are made if you don't do what's first, then all of a sudden you really don't know what you're working with. And then finally, the solution stage. I think this is the solution stage. Which statement is correct concerning the relationship between extreme points, feasible points, and optimal solutions in LP? Okay, and if you remember in that first lecture, I had a graph. In that graph, we had a feasible region, we had the constraints, we had the corner point, which is the same as an extreme point, and all the points in the feasible region satisfy all of the constraints, and then one of those points will be optimal. One or more points will be optimal. Okay, so this is just that relationship between these three things: extreme points, feasible points, and optimal solutions. Okay, and there's usually more than one extreme point. There's more than one feasible points, and there can be more than one optimal solution, which turns out to be a point in the measurement space. Okay, question 4. Okay. Oh, good question. When should we expect homework 1 to be graded? I thought I had graded it. I'll check right after this. Let me write this down. If I haven't graded it, I'll grade it. I thought I did. Okay. Homework grade. I thought I did. I'll double check after this. Thanks, Omar. Okay, which statement is always correct for any feasible point? Okay, and the key here is any feasible point. Any feasible point. Is any point optimal? Is any feasible point an extreme point? Is any feasible point, are all the constraints satisfied? Any feasible point will satisfy all the constraints. The value of the objective function will be non-negative for any feasible point. And the slack or surplus of at least one constraint for any feasible point, is it always 0? Okay, which one of these, how many of those statements would be correct? Okay, and so it's just thinking about logically, you have this space, you have this point, feasible point, well, how many of those things are correct? So a lot of this is just in language and in logic, and so a lot of mistakes are made by Roger in making statements that are always true. Okay, then we get into the mechanics, a little bit of the mechanics. Which formulation is correct for the product mix definition? And I have A, B, C, D, and E down here. And so here it's just defining, the definition is given in a table, and this is the product mix definition. And I took the one right out of the notes. Hopefully there's no problem with this. Here's how much wood is needed for each table and chair. Here's how many hours are needed. And here's the profit for each table and chair. And over here's the capacity in board feet and hours for the tables and chairs. And so the question is, when you take this definition in tabular form and you formulate it, the second stage, which one of these formulations will be correct? Okay, and in the formulation, you have to be careful with a number of things. 1, the actual numbers are in the right place. 2, the inequalities are in the right place. And 3, the inequalities of the non-negativity constraints are in the right place. Okay, so usually those are the 3 things I looked at. Okay, are they in there? And also the numbers for the objective function and the number for the constraint sets, and the number for the capacity is for the wood and labor, and the directions are right. Okay. What does the number 30 represent? Now, this is going to be important for the homework, as we'll see, but it's even more important for the memo coming up. Recognize that the definition is the number of resources for each product. And that definition is going to be important. I've already said that, but which one of these then is the correct statement of what I just said? Okay, in the product mix definition, what is the profit if 1 table and 5 chairs are produced? And so in the tables here, we have 1. Chairs, we have 5. So the question is, what's the actual total profit? Okay, well, it's 1 times 9 plus 5 times 4. And you add it up. It's one of those numbers. In the product mix definition, if only tables are produced and 0 chairs were produced, what would be the optimal profit? So now we're optimizing this with 1 variable. And so this is a good question because it focuses on what is the concept of optimization. So let's look at this. Only tables, 0 chairs. So essentially this chairs here, we can delete that. It goes away. And so you say if only tables, and this is your capacity, this is the how many resources are needed for each table. So I tell you what, let's come up here and let's do this. Oh, let's make this a little bigger. Yeehaw. To the window, let's make it bigger. Okay, and let's do it again. Auto fit, fixed. Now bring this in. Bring this in. Wow. Maybe I should have done this. Bing, bing. Yeehaw. Okay. This is not cooperating, is it? I didn't think I would have this much problem. Okay. Wow. Live TV here. Let's take this. Boom, boom, boom. Boom, boom, boom down to here. Come back here. And let's increase the width of these things. There we go. Okay. Now, what is the map? Oh, no. Let's come down here. Wow. Here we go. And we want the max. What's the maximum production that we can make from tables using just the wood, regardless of the labor? And so if we have 300 capacity and 30 board feet of wood for each table, well, 300 divided by 30, what is that? A maximum of 10? So we can make a maximum of 10 tables using all of our wood. Is that correct? I think that's true. Okay. If we use all of our labor for 110 divided by 5, that's going to be 22. Is that right? 5 into 110 is 22? Yep. So what's the maximum profit that we can make? Well, before we get the maximum profit, the number of tables that are maximum, notice right here, we do not have enough wood to make 22 tables. But we have more than enough labor to make 10 tables. And so you take the maximum number of tables that can be made, multiply that by 9 to get the answer. Okay, hopefully everyone got that. It took me a while to put it in the word here. Okay. Okay, number 9. What is the solution? Okay, now we go to actually solving an LP. And I have a simple one here that's going to be just 2 dimensions, x and y. And you can solve it by hand or you can solve it with Excel. I'd recommend solving it with Excel. It's pretty easy that way. and I was hoping everyone would set it up like that. These are the non-negativity constraints. That's no problem. We have one constraint, okay? And so I'm easing into this. So let's bring up Excel. Here we go. Let's bring this over here and enlarge this. Okay. And so right here we're going to have X and Y, and then we're going to have the right hand. Then we're down here, we're going to have the objective function, well, the values. Okay, and these are going to be my decision variables. Okay, let's see here. Yeah, I'll look at homework one afterward. Wording question: needed and used are often interchanged. Right or wrong? From an operations perspective, what do these mean? Well, it depends on the context, Craig. What is the context? Is it up here somewhere? Did I use it up here somewhere? To answer your question, I would say depends on the context. I would say depend on what when need is used and when used is used. Okay, let's bring back Excel here. Okay, there's my let's shade this in a little bit. There's my decision variables. Center this. Okay, and then here's the value. There's the objective function. The objective function is 8 and 5. And over here is going to be the value of the objective function, then subject to my constraint set. And then the coefficient of my constraint set is 15 and 10. And then the right-hand side over here is going to be 30. Okay? And so here I just want to say sum product of these two, comma, and the value of my variables, F4 to fix, return, and then copy this down to the next one down here. Delete that. And now I'm ready to solve this thing with data, solver, and my objective function is going to be this value right here. That's the value. See, here's my set of my objective. There's the value of my objective function for x and y. Well, x I want to maximize. So right here, my changing variables, I'm going to change those variables. Those are my decision variables. I'm going to add a constraint. Here I just have one constraint, and that is the left-hand side is less than or equal to the right-hand side, which is 30. And then I say OK, and then I say non-negativity constraints. I want simplex LP, and then solve. And then if you solve this thing, there's a solution and there's the value. And so hopefully everyone will be able to actually solve that. Oh, notice I say, what is the solution? Now remember, the solution to an LP is the point or points which in the constraint set would satisfy the objective function. And so it's not the value of the value of an objective function is not a point. It's the value of an expression. So the point in 2 dimensions is either x, y, a, b, or d. So one of those 3 would be the answer. Oh, I see what you're saying. What does the number 30 represent in the product mix problem? The number of board feet of wood needed for each table and the number of board feet used in the production process. The number of tables produced for each board foot of wood, the number of tables that can be made with the capacity, number of tables produced the unit process. Yeah, needed and used. Yeah, in this case, it's going to be used interchangeably. The number of board feet needed and the amount of board feet used, the number then is what you need, and the amount is what you're going to be using. And so I kind of matched similar connotation of words together. But needed and used can be used interchangeably. Okay, and I say the production process, that means in the making all of your tables and chairs. So the whole production process, not producing one table, but producing however many tables you can. Okay, because it's a product mix problem. Okay. And then we come to 3 dimensions. And we have a less than constraint, greater than constraint, less than constraint, equality constraint. We have 3 variables, and solve it again. But this time I say, what's the value of the objective function at the optimal solution? So here, what is the solution, which will be a point? Here is the value of the objective function at the optimal solution. And so that's just going to be one number. And we're going to set this up pretty much the same as we did before, right? And so in this case, we're going to have x, y, and z. Put it right here. X, y, z. And then we're going to have down here. Here's going to be our, shade this in for our decision variables. Our objective function then, just move this over, you can see it, is 895. This is going to be 895. Okay. Subject to, this is going to be 16, 32, 26, 22. This is going to be 28, 12, 35, and 20. This is going to be 32, 24, 12, and 24. And then over here, the right-hand side, hello, there we go. Oh, 90 all the way. That makes it easy. This is, oh, let's put it over here. 90, 90, 90, and 90. But notice that it's less than, greater than, less than equality. So let's put this in here. Less than, greater than, less than, equality. So we have to be careful with these things. So let's move this over. Okay, and this will be the left-hand side. Okay, now we're going to set up these values here. Equals the sum product of our coefficients, 1, 2, 3, comma, our variables, x, y, z, F4, to fix them so they don't move, and then copy this down. There we go. Okay, we don't need this. Delete. So then we come to data and solver. Okay, now our objective function is down here. Boom. That's our objective function. Here, set objective, that cell right there. I want to maximize, do I not? Yes, I want to maximize. And then my decision variables are these 3 right here. 1, 2, 3. There we go. And let's delete this. That's no longer a constraint set. Constraints down here. Now we're going to add. Okay, first of all, it's less than. It's the left-hand side here is less than or equal to the right-hand side. Add. The left-hand side is right here greater than or equal to the right-hand side. Add. The left-hand side is less than or equal to the right-hand side. Add. The left-hand side is equal to, boom, the right-hand side. Okay. Non-negativity, simplex algorithm, boom, say solve. When I say solve, then the answer is going to be in that cell right there, the value of my objective function. That's how you solve it. That's how you solve it with Excel. So we're setting it up, step at a time. This is the mechanics. Okay? I'll let you finish it. I don't want to steal your thunder. Okay? There we go. So there's the quiz. And let's go on to the homework. And if anyone has any questions on the quiz, you can certainly ask them, and I'll go back. I'll go back to the quiz. But let's go to the homework. The homework now is more of the applications. And you'll see what I mean. Some good applications in here. Okay. get my file set up here. Here we go. Okay, here we go. So part A, a little bit of a scenario to ease into this. The Golden Company is planning the production of 2 products in a popular product line. They collected the following information. And I'm making this generic now. Product X and Y have 3 resources. There's a capacity, there's the profit, and there's the production standards. How many resources are needed for each unit of product? You have been designated as the analyst to respond to their request. Glenda, chairman of the production planning committee, was first interested in the optimal product mix that produces the maximum profit without exceeding capacity. What's the profit from the optimal mix? Okay, essentially just solving it. Okay, let's bring back Excel. Let's open a new sheet here. And then let's take the problem here. Let me just take the problem here. Take this problem here, Control C, and copy this. And then open Excel back up here, bring it back, and then come down a little ways and say Control V and paste it. Control C, make sure that it's numerical. Okay. And we just want to solve this thing. So essentially, from this, we just want to solve it. So we can solve it with keeping what we have here. Let's, I like Arial, font of Arial. It's bolder. 10's good enough. Okay, and let's center these things. There we go. So down here, let's have the value. I'm sorry. Let's see. Wait a minute. Yeah, here's the value of my product X and Y. So this is going to be mixed up a little bit, but we've done it before. We know what we're looking at. We know what we want. So up here, let's put a value here. This will equal the sum product of these coefficients, comma, the value of my decision variables. Whoops. F4 to fix. Okay. I want this back up again. And let's make both of those live to F4 to fix both of them. There we go. And then return. And then copy this down for resource 1, resource 2, resource 3, and then finally my profit. So this right here, let me bold that. That's going to be my objective function right there. Right? And this is going to be my value of my let's make this a number. Just to be safe. Okay, this is going to be the value of my objective function. And over here, this is going to be the my decision variables. So the first thing we do, we will just solve it. Okay, and we've solved it before. Data, solver. The objective function is going to be value of the profit is going to be that. Max subject to my variables. I'm going to add my constraint sets, but this time they're all less than. So the value is less than or equal to my capacity. I say OK. Non-negativity, the simplex algorithm, solve. I'll let you do that to get the answers. Okay, so let's bring this down, and that's going to be the first one. And so that answer, that's how to get the first answer. Okay, number 2, the committee requested information about the utilization of resources at the optimum product mix. Specifically, they wanted to know which resources had capacity remaining. Which resource has the maximum remaining capacity? Now remember, this is at the optimal product mix. So let's bring back Excel. And here at this optimal product mix over here, I want, they're all less than, so I want the slack. So that's going to equal the capacity minus the value. And I bring this down, okay, And so at the optimal solution, once we solve this thing, then there's our slack. And so and this is remaining capacity after the optimal solution. At the optimal solution, it's our remaining capacity. So that's what we're saying. At the optimal solution, which resource has the maximum remaining capacity? So essentially, you solve this thing and see which one of these numbers are the greatest, and that really that will correspond to the resource with the maximum remaining capacity. Okay. For example, if I made one product X and one product Y, the maximum remaining capacity is going to be resource 1. Okay, if I made 2 resource X and 100 resource Y, I don't want to do that. 50, 40, 20, then resource 1 is the maximum. Okay, if I do 21, then resource 3 is the maximum. Anyway, but they want to know this at the optimal solution. Okay, let's go on to the next one. The utilization of resources was important to Al, since he was head of material management, which included resource capacity. Since Al frequently requested hypothetical situations to gain insight in resource utilization, Al proposed an alternative. Purely for comparison purposes with the optimal solution, what would the impact on the utilization of resources, what would be the impact on the utilization of resources if we produced 12 units of product X and 18 units of product Y? Now, which statement is true about the resources? Okay, so let's look at this. I see what Al is saying. Let's bring back Excel again. And so over here is Al. And what Al is saying here, he says he wants 12 and 18 here. Isn't that what he said? 12 and 18? Oh, let's see here. He says 12 of X and 18 of Y. Yes, yeah, that's what he said. 12 of X, 18 of Y. So if I do that, then over here, I'm going to say, okay, then over here, I'm going to have some product at that mix, Al's mix, of my coefficients, comma, Al's mix, F4 to fix, in parentheses, and copy that down. Bing, 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 bada bing. So and then we have Al slack. And that's going to equal my capacity minus that number there will be the slack. I'm not going to do it. You can see how to do it. So instead, I'm going to say 2 and 3. I'll do it that way because I don't want to give away the answer. Again, I don't want to steal your thunder. That's going to equal the capacity minus Al's right-hand side, how much Al is using. And you copy that down. So there's the slack. That's the resources. So if you put 12 and 18 here, then this is what Al wants to know. Okay, compared with this slack. So Al slack compared with the optimal slack. That's what Al is asking. Resource 1, 2, 3, 1 will have the greatest slack, and resource 2, 3, 2, 3 will have the smallest slack. Which is the greatest? Which is the smallest? Okay. Number 4, representatives from the sales department reacted to the possible production amounts by proposing minimum requirements to meet their customers' future needs. Isn't that true of salesmen? If I'm going to sell, I want the products so that they can sell them. And so, who is this? Charles wanted to add a minimum production requirement of 18 to product X. Dan wanted to add a minimum product requirement of 18 to product Y. So Charles and Dan, they say, look, I'm going to go out there and sell at least 18. I want to sell as many as 18. So I want to have 18 out there ready to go because I can do that day one. So they're pretty confident. And so look, operations, make sure those products are there because I want to sell them. So Ellen cautioned, well, that will not be feasible. Well, I don't think it will be feasible if they are both applied together. I'm not sure if each one is infeasible if applied alone. We need to examine the impact of these requests. At this point, you were asked to determine the feasibility of the request. Which statement is true? And notice how I said this. Satisfying the request from Charles and David together will result in a feasible problem. So they both can be done together. Satisfying them both together will be infeasible. You can't do it. Satisfying Charles and not Dan will be infeasible. Satisfying Dan but not Charles will be infeasible. Satisfying the request from Charles and Dan together will result in both a feasible and infeasible problem. Well, I put in there just to make 5 answers. E is not an answer. Okay, anyway. You know, as I said this, there's a typo here. This should be feasible, and this should be feasible, because these, oh, no, they're not. Yeah, now see, these should be feasible. So that's a mistake. These are mistakes. I typed this out and I changed it around. I forgot to take out the in. This should be feasible and this should be feasible. But I answer it the way it is. So as it turns out, B, C, or D is going to be correct. Let me just do it. See, now this is a mistake I made when I typed this stuff up. Okay, let's bring this up. Now, what are they doing? 18? 18 and 18, okay? Let me show you how to do this. We have Charles and Dan. They want 18 and 18. Whoops. 18 and 18. Wait a minute here. Let me get this right. Charles wanted to add a minimum production requirement of 18 to product X. And Dan wanted minimum product 18 for product Y. Okay. So let's do it this way. So we have 18 for X for Charles, 18 for Dan, and make these 0. So can it be done? It's a good question. Can it be done? Well, if it can be done, then that means Y is going to be 0, and Dan will be 0 for this. And so can it be done? I don't know. Let's come over here and see. So this is going to be Charles. Charles, whoops, slack. And this is, whoops, Charles, slack. This is Dan's slack. Okay. So I'm going to do this all together. That's going to equal the capacity minus the sum product of my product X and Y, comma, 18 and 0, F4. So let's do the same thing for Dan. That's going to equal the capacity minus the sum product of the coefficients, comma, times 0, 18. Whoops. 0, 18. F4. Keep forgetting that. Now I can copy these down. As I copy these down, I noticed, boom, boom, boom. Feasible, feasible. Now what if you did them both together? Okay. C and D. That means 18 and 18. Okay, this is C and D. Same thing. Equals sum product of the right-hand side minus the coefficients, comma, the Charles and Dan together, F4, and then copy this down. That doesn't look right. Something's wrong. Equals sum product, I'm going too fast here, oops, equal the right-hand side minus the value of the left, equals the right-hand side minus the value of the left-hand side, which is the sum product of the coefficients, comma, the product mix, F4 to freeze. That should be, that looks right, that feels right. So I bring this down, boom, negative. See, that negative slack indicates infeasibility. It's because you don't have enough resource 2. Resource 2, you need 18 more capacity of resource 2 to do both of these together. So that negative indicates an infeasible solution. These positive indicates a feasible solution. Okay, and so notice using them both together, it's infeasible. Each one separately would be feasible. And that's how you would solve this problem. Now the reason I went ahead and solved it for you, if you look at these here, I say satisfying together will be feasible. No, it's not. It will be infeasible, so B is correct. Okay, but notice satisfying the request from Charles only will result in an infeasible. Actually, that's not right. It's feasible. Satisfying from Dan only and not Charles will be feasible. So that's correct. Oh, I see. Satisfying, okay, so the answer is B. You know, I thought C and D would be the answer, but if this was, I changed it. I remember I had feasible. I says, wait a minute, that means all three are right. If this was feasible, then these two would be right too. Okay, but it's not. Whoops. Okay, so that one, the answer is B on that one. Okay, Gail, okay, this is a good one. Gail suggested the requirements for that for every product of X, there must be 2 product Y's produced. The committee was concerned that the additional constraint would reduce the profit significantly. When you start putting more constraints on it, you have more things you have to do, and it's going to move away from optimality, which is reduce the profit. Gail disagreed. If the profit is optimized with the additional constraint she suggested, what is the reduction in profit at the optimal LP solution with the constraint suggested by Gail? Okay, and so this one, got to be careful. Every product of Y, there must be 2. Every product of X, there must be 2 products of Y. Okay, so there's 2 things going on here. Either you have, so you want X, whoops, so the constraint is either 2X plus Y equals 0, well, plus Y equals 0, or you're going to have X plus 2Y equals 0. So you have one of those, and who knows which it is. Okay. In other words, when you add an extra constraint that every X there must be 2Y, okay, well, which one of these is correct? Well, let's do this. Let's analyze this a little bit. You come across here and say, okay, let's put values in here for X and Y. Okay, here. So what if X equals 1? If X equals 1, then what is Y going to equal? Well, let's do it this way. Let's do it this way. I'm getting ahead of myself. X equals this equals. Okay, it's one of these 2. You're right, Becca. You're right. I got ahead of myself. And so, so which one should it be? If X is 1, then y is going to be 2. Okay, and here, if y is 1, and coming back here, then x is going to be 2. If y is 1, x is 2. So you got to be careful. For every x, there should be 2y. Initially, people say for every x, there's 2y. Well, mathematically, it sounds like that's what you're saying. But as it turns out, for every x, there's 2y, should be 2x equals y. So what is stated in a sentence, you have to be very careful when you represent it in an equation. So if you have 1x, you want 2y. And so this is the relationship. And so Becca, you're right. So what this would be, you come out here, you have 2x minus y equals 0. So this is our constraint. 2x minus y is 0. So let's bring back Excel. Okay, and then let's enlarge this. So now down here, let's add another row here. And now we have the 2x equals y. Isn't that what it was? 2x equals y, correct. And it's 2x minus 1y. And so the way this is going to be is 2x and a minus 1y, and it's going to be equal to 0. Okay, so we're going to bring this down again. So now, when we go to solver, let's reset it all so we don't make any mistakes. The objective function is still going to be, where are we? Right here. Boom. Max, by changing these variables, same variables, by adding these constraints, and if I remember right, aren't the constraints all less than or equal to? Yes, I'm pretty sure they are. And so the value here of these three, 1, 2, 3, are going to be less than or equal to its capacity, 1, 2, 3. But now we're going to add an equality constraint, where the left-hand side here is going to be equal to, and I'll just say 0. I could have clicked that, but it's 0. I say OK. Non-negativity, simplex, I say solve, and then that'll give me the answer down here. But it will also give me the value of the objective function. I'll take this value, the last value, take the difference, and that's what I'm asking. Okay, and I'll let you do that. Okay, we're getting there. Oh, and I don't even ask for the number. It says, is it less than 10, 10 to 50, 50 to 80, 80 to 100, 100 to, you know, where is it? Okay, and this is just looking at these relationships. So now notice I'm getting more into, well, usually if you make a table, you want 4 chairs, because if you're going to buy a table, you're going to buy 4 chairs. And so, yeah, maybe we need to have these kinds of constraints in there. So Gail is probably right. And so the demand may not be exactly that, but it'll be close. 2 to 1, 4 to 1, 3 to 1, something like that. Okay, if you're selling a wagon, you want to sell 4 wheels, unless people want to buy a wagon without any wheels. Okay, 6, Roger. I love Roger. Great device. I love this device. Roger, after hearing suggestions from practically everyone on the committee, interjects. One analysis we have not considered is a result of changing the unit profit values for the products. And I'm going to highlight this, the unit profit values. And the reason I'm going to highlight that is that this is what he's talking about. If the unit profit value for one product relative to the other is changed enough, and let me highlight that, is changed enough, and I'll underline that, then a different optimal mix can be obtained. If the unit profit value of one product relative to another is changed, no matter how small, and let me highlight that, and that's the key, if it's changed enough or no matter how small, so one is big enough, the other is really small, then the optimal mix will begin to gradually change from one extreme point to another extreme point. If a new optimal solution is obtained from changing the unit profit value of one product relative to the other, then the maximum profit will always be at only one extreme point. Then the optimal profit will be at only one extreme point. And let me underline that. Is that true? But if a new optimal solution is obtained from changing the unit profit value of one product relative to the other, then the optimal solution will always be feasible. And let me underline that. So essentially, Roger is making four statements here. The question is, how many of them are correct? And they're all probably not correct. Now, these are the unit profit values. Let's bring back Excel. So be aware that he's talking about these profit values down here, 24 and 44. That's what he's talking about. So if I change this a little bit, and what I suggest, and I'll let you do this, what I suggest is do it. Change them. In other words, go back to the original problem. Okay, and let me go back. Can't go back. Well, I can. Let me erase this. Okay, go back to the original problem, and then say, hey, you know, what if I change this to whatever the answer is? So this, let me just say, this answer is X, and this answer is Y. Whoops, this is X. This answer is Y. Okay, those are the answers. But then if I change this to $24.10 and then solve it again, are those numbers going to change? Try it. See what happens. But if I change this enough to, let's say, $240 and then solve it, will these numbers change? So if it's changed enough, or it's changed no matter how small, then those numbers will change. Okay, so try it out and see. And then the other questions he says about the extreme point, at only one extreme point, well, we talked about multiple solutions. And so when you start moving it, and start moving from one extreme point to the other, there's going to be a point when two extreme points will be optimal. And then will it always be feasible? Well, you have to be feasible to be optimal. Okay, so here's where a lot of people in business will say things wrong, go down the wrong path and get wrong answers. Also in conversation, people will say things and you don't have to correct them, but you pretty much know very quickly what they know and what they don't know. And so you have to be careful with people who talk about things they don't know, and you'll know that they don't know. And so you have to be very, very careful. Okay, let's go on and solve some other things. Now the silver company, I just moved to 4 products here, and I have the different departments, wiring, drilling, assembly, and inspection. The silver company is planning the monthly production of technical products required as part of their NASA 3-year project. Sounds like Roger wants to sound important. Yes. I don't want to go off a tangent. It's really easy to, but that just brings up a good point. In business, you're working with personalities. And a lot of times you're working with ego. And a lot of times you have to temper what people are saying based on their ego or their personality or their temperament. Why are they saying that? Are they saying it to help? Or are they saying it to just for their own benefit, to sound important? Okay, and so you got to be careful. Okay, each product must pass through each department: wiring, drilling, assembly, and inspection. The times to produce one product for each department are presented below, along with a monthly capacity in hours for each department for this project. So here's the time required, and here's the capacity in hours. Although the maximum level of production or a specified level of production for each product are not required. The minimum level of production is 90 for each product. So we're going to have a minimum production of 90 according to the contract. The unit profit from production has been determined and presented in the table below. So they're saying, here's our unit profit per item produced. And we have to make at least 90 for each one. But which one do we go over 90 and how much to maximize profit? What is the maximum profit? Which resource has the greatest amount of hours not utilized? In other words, the minimum. And hopefully some of them are zero. They're binding. And what's the profit? Okay, so first we do that. Okay, so now let's bring back Excel. A new spreadsheet. Let's come over here. And let's take these numbers here. I'll go ahead and take these right here. Control C. Come back here. Come down here, Control V. Let's go down one more. There they are. And this is, don't know what these, oh, I guess I could just take these two. I guess I could take these two and add these in. Bing, 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 bing. Paste. And then the 27, 24, we have this. Control C. Then bring this back. And bring this down here. Whoops. And put it here. Cancel. What did I do? 1, 2, 3, 4. There it is. Okay, and also we have a minimum production, oops, of 90. Here we go. So I copied this over, I put 90 in there. Okay, and let's make these Arial. Let's center them. Make them 10, and make these numbers currency. Let's go to numbers. Okay, there they are, and this is profit. Okay, and here's our capacity, and over here will be the values. Okay, again, we'll take the sum product. If we're going to set this up again, we'll do it again, but this time we're taking more. Whoops. Product of the coefficients, comma, the values. I'll put the values right there. F4. Here's our values. Forgot to put those in. There they are. Ka-ching. And copy these down all the way down to here. This one is not important. This one is our profit. This is our profit. Okay. Okay, and then we can box these in. Okay, then I think we're good to go. We go data, solver. Our objective function now is going to be right here. Boom. We want to maximize our profit by changing these cells right here. 1, 2, 3, 4. Okay. And now our constraint set, we're going to add a constraint. Well, first of all, we have our product mix constraint. All these values here are less than or equal to our capacity. These values here. So we know that. But also, we want to say, well, wait a minute now. These values that we're going to produce or mix has to be greater than or equal to a 90, because that's a minimum production. So now our constraint is going to be on the actual decision variables. They have to be 90 or more. We're not going to zero out any one of these. So the minimum will be 90. Say, okay, and then non-negativity constraints, make sure it's a simplex algorithm, and then boom, solve it. So I'm not going to solve it. I'll let you do that. Okay. Now let's come back And what's the maximum profit? Which resource has the amount of hours not utilized? Has the greatest amount of hours not utilized? Well, there, again, we have slack. That equals our capacity minus our values, and then copy that down. Okay, which one is the greatest amount not used, that kind of thing. Okay, what is the profit for the mix that is exactly 50% above the minimum production level for each product? Okay, so here they're saying, well, we can calculate them. Well, what about just having 50% above that minimum? And as it turns out, there's a number of reasons for having a set amount. Okay, and so these values here will be equals 1.5 times the 90. And so this, well, I can copy this over, and then I'll have the profit here, I'll have the slack, blah, 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 blah. I'll let you do that. That's all there is to that. And what's the profit? Okay, now then, environmental compliance. So now this is going to be an ingredient mix problem, but instead of ingredient mix, because that's pretty popular, but I wanted to go into sustainability and looking at carbon footprints and environmental compliance. This is a very practical LP. A company owns 3 factories on the Washita River that emits 4 different pollutants. Pollutants 1, 2, 3, 4. The 3 factories, A, B, C. The state has recently mandated a 16-ton reduction for each pollutant in the river. So let's go ahead and set this in here. I'll go right here and say reduction in tons is going to be 16. 1, 2, 3, 4. Okay, a 16-ton reduction for each pollutant. For each pollutant, not total, but each. The company is considering the tons of emissions to process from each factory that will reduce the amount of pollutants in the river that meet state requirements for each pollutant. The tons of emissions to process from each factory. So down here, let's go ahead and take this and go below. And here are the tons. I'll say mix in tons. In other words, the tons of emissions to process from each factory. Let me underline that. Okay, and so the concept here, I think I mentioned this in the lecture, the concept is you have these 3 factories, and this is going into the river. The river is the product, essentially. And then when they go in, the pollutants is what we're trying to reduce. That's what we're examining. Becca. A little confused by why the 1.5 times 90 is replacing the value for the problem 9 if we have time to revisit. Oh, absolutely. Sure. Let's back up here. What is the profit for the mix that is exactly 50% above the minimum? Well, the minimum is 90. So what's 50% of 90? It's 1/2. So we're taking 90 plus 1/2. So essentially, what this 50% above the minimum will be the minimum, which is 90, times 1 plus 0.5, which is 50% above 90. In other words, it's 90 plus 0.5 times 90. Well, that's equivalent to 1.5 times 90. See, it's 1 times 90 and 0.5 times 90. You add 45 to 90, get 50% more. I hope I said that clear enough. I did go through it kind of fast. The minimum is 90. That's given. 50% of 90 is 0.590, and 50% more than the minimum would be 50% of 90 plus 90, and that's 50% above 90. If not, ask again, and we'll go back and do it again. Okay, so now coming back to this, so the question is, the setup here, the concept is that the Washita River is the product. The company, 3 factories are emitting emissions going into the product, but then the product has some requirements, the pollutants, and we have an objective over here of reduction in tons. Okay, and so this is how many tons are being processed going into the river. Okay, and when you process, you'll reduce the pollutants, and we want to achieve 16 on each of these pollutants. But now these numbers in here, these are the tons of pollutant reduced per ton of emission processed. So if I have a 1, 1, and 1 here, if I have 1, 1, and 1, that means pollutant 1 would be 0.3, 0.2, 0.4, what is that? 4, 5, 6, 7, 8, 9. 0.9 tons reduced is all it's going to be done. But we want to get up to 16. So we have to produce a lot more than just 1. Okay, so that's the setup. The maximum tonnage that can be processed by a factory is 280 tons. Aha. So now let's bring this down. And now we have a maximum of 280. So this mix cannot go above 280. Okay. So this is a very simple environmental compliance. And by the way, this is pollutants going into a river. This could be going into the air. This could be going into a food source. This could be contaminants going into any type of forestry. This could be any kind of thing going on into actually a food product, Food and Drug Administration. And so all these things are even in meat and beef and cattle. So this kind of a problem, once you get the structure and take out the definitions, put other definitions, you can apply this to a lot of other types of problems. Very good problems. Okay, so let's solve this thing. Let me set it up and solve it. I think I have everything in here, if I can remember everything right. So let's take this. Let's take all of this. Control C. Let's bring Excel back. Open up another sheet here. Come down here and say Control V and paste this thing. Okay, and I think I have it pretty much set up there. At least close enough. Okay, here's my decision variables, correct? Okay, and this is going to be the cost. Okay, and let me go ahead and shade that too. This is the cost. Here's my decision variables. That's what I'm changing. Here's my cost to minimize my cost to achieve these goals. And this is a constraint on the mix. So let's go to the data, come to the solver, bring it over here. My objective function is going to be the cost. Now I want to minimize the cost. So this cell right here is that cell right there, which is the whoops, close. That's not true. I'm going too fast here, guys. I got to do the values. Equals sum product of the coefficients per ton, comma, times the mix in tons, F4. That's what I need. And this is how many, this is how much pollutant will be reduced if you have that many tons of processed from A, B, and C. Come all the way down to here, and there's going to be my objective function. Right? You know, I can make that another color. Make it blue, make it red. Okay, I'm messing around here. We want to go to bed, don't we? Okay, Let's see here. We want to shut down here. Let me go back to my pet things here, and then center. Format. Now let's bring in solver, data, solver. Here we go. And now my objective function is going to be that right there. I want to minimize, as we say, minimize cost by changing the cells, by changing these cells, 1, 2, and 3. Okay, I'm going to add my constraint set, but now notice the left-hand side, or the values of the amount of pollutants that are being reduced, we want that to be greater than or equal to the 16. Now, since 16 is the same, I could have just typed 16 in there, but I'll do it this way. Okay? Then I want to add also the mix of tons is less than or equal to the 280, because I can't go above 280. That makes sense? Okay, let me make sure I have everything done here. Sounds good to me. Looks pretty darn good to me. Okay, and then I say okay. Non-negativity, make sure it's a simplex array. Notice it goes back to nonlinear. It goes back to this GOG nonlinear. Make sure it's simplex, and then boom, solve, and they'll give you the answer. Okay? And I'll let you do that. Very good. Okay. What is the minimum cost to meet the state requirements? Which pollutant has its mandate exceeded the greatest at the optimal solution? And which one was the best? And which one had it exceeded the most? Okay, let's bring this back. And there's where you get the surplus, right? Equals the value minus the actual right-hand side. And so right now, these have to be positive. The one with the greatest positive have the minimum exceeded the most. I got some questions here. Okay, let's come back. Anyway, so then you solve it. Let me finish this, then I'll go back to these questions. We'll go back to these questions talking about the other problem. I think it's a silver project. Okay, then it says, suppose the maximum tonnage, which is 280, that can be processed by a factory was relaxed, where there was no limit on tons processed by a factory. If only one factory was used, which factory would yield the least cost and meet state requirements? Okay, Craig, why is it surplus when all the others have been slack? Because here I want the requirement. Let's see here. This is a reduction, and I want to reduce the tons of pollutant at least 16. So I want to reduce it more than 16. So since my value is going to be more than 16, that is the value of my constraint is more than the requirement. So therefore it's a surplus. So this is a minimization problem. It's an ingredient mix problem. Ingredient mix. So we're maximizing or we're minimizing, but it's over the greater than constraints. So these constraints are greater than. So if I go back to let's go back here for a minute. Yeah. Then for ingredient mix, and here it is, ingredient mix. So notice it's greater than constraints. And so here, these are requirements, minimum daily requirements. The other is minimum daily minimum tonnage that's reduced. We want to reduce more than that. Okay, like if you can reduce all of it, or at least 16. Reduce it by 16. You can reduce it more than that, but 16 isn't much. So this is greater than constraints, and we're minimizing. So that's the idea on this one. And so notice it's conceptualizing the problem. It's understanding the problem. So right here, I could take these numbers here and go this way. So these are the values. This is the right-hand side. And so essentially, these are going to be greater than or equal to this right here. Okay, because what you're reducing has to be more than 16. If I'm minimizing the cost and this was less than, if it was the other way, well then I'll produce nothing. And I'm not going to reduce it at all. And so my reduction is going to be 0. But I want to reduce it more than 16 because that's a mandate. Reducing it more than 16 requires money to actually process these emissions. Okay. And so like if I had 1 ton here, 1 ton here, and 1 ton here, let's say 2 tons here and 3 tons here, let's say 5 tons, 55, 555. Now all of a sudden, whoops, I'm trying to get my surplus above 555, 555. Okay, and so there you can see these two are the same. This one is this one's the lowest. These two are the highest. Blah blah blah. Okay, and this is 234, 234. So if I had this 7, if I had this 567, then this is going to be the highest. That kind of thing. So we're reducing it by 50 tons. 16 is the requirement, but 50 tons. This brings up another point, going a little bit beyond the problem, is that this can be used to say you can minimize your cost, but this may not be the only factory on this river, the Ouachita River, as an example. There are other factories that are emitting pollutants in the river, and there's a mandate. But then again, if you can minimize this, you know exactly your minimum cost. But then you say, what if I made this 17? That means I have 4 tons that I could sell as a carbon offset or a pollution offset to some of these other companies that don't have the capability to reduce it. And so you go on to an offset marketplace and sell it. And so you certainly can do that, and people do. And this is becoming more and more of an issue in a stock market. Oh, you're right. 280, 280, 280. You're right. If I did 280, then it would be reasonable. You're right, Raphael. Yeah. I was giving examples. I'm trying to make these positive, okay, without solving them. Okay. Let's go on. Okay. So hopefully, if not, just go back and ask more questions. Suppose the maximum tonnage that can be processed by a factory was relaxed. So suppose they say, okay, let's forget the 280. You can reduce as much as you want. There was no limit on the tons processed by a factory. But if only one factory was used, which factory would yield the least cost and meet the state requirements. Interesting. So how would we do that? Well, let's bring this back. So what this is saying is only one of these factors can be used. But then again, if only factory A is used and we want to meet these reduction requirements, then the question is, well, pollutants 1, 2, 3, and 4, how many tons are required to be processed to reduce the first pollutant by 16 tons? Okay, well, that's going to be 16 divided by 0.03. Yes, because 3 times 0.03 is 16 tons. I could do the same thing. Okay. But then again, I want to make sure that I want to minimize my cost. So which one do I pick here? Well, if I process 533, is that enough tons to process to reduce the second? Yeah, I only need 400. What about the third? No, I need 800. What about the fourth? I need 1600. So how many do I have to process in order for all 4 of these to meet their required reduction in tons? It's going to be the maximum. The maximum of this is how many I have to, equal max. It's going to be the maximum of these. That's how many, for crying out loud, there we go. There we go, max. That's how many I have to produce from A in order to do that. But how much does that cost? Well, that's easy. The cost per ton is $250. I have to produce 1,600, and so there's my cost for A. I do the same thing for B. I do the same thing for C. And then I come over here and say, okay, well, if only one factor is used, which factor would yield the least cost to meet state requirements? And so which one of these is the least? It's either going to be A, B, or C, or 2 of them, or 3 of them. As it turns out, only one of them it will be the least cost. And I'll let you figure out which one it is. Okay, now the assignment problem. On the assignment problem, a bank assignment. So in the assignment problem, it's like a transportation problem. Remember the transportation problem, you had sources and destinations. You're shipping from point A to point B, or point A, B, and C to 1, 2, 3, 4. You're shipping from one place to another, and it costs money to ship from here to there. Well, you can also have an assignment problem, which is very similar in structure. Again, the structure defines a transportation problem, but now you're not transporting goods or information or people. What you're transforming, or what you're transporting, is work from one place to another. Is called the assignment problem. You're assigning work from one place to the other. Well, I decided to go a bank. A bank distributes checks to different sites to be processed. So I'm transporting a check to a site to be processed, and it costs money to process it. Within a large metro area, each site has the capacity to process different amounts of checks per day. Let's see here. There's the capacity. It can only produce that many checks a day. The checks that need to be processed each day are payroll, personal payroll, draft, government. The total demand is different for each type of check. Over here is the demand. And the cost to process each type of check varies with the site. And these values are summarized in the table. Here's how much it cost per check. Okay, and notice I just randomly put numbers in there. A lot of times they're the same in companies, but if you have different branches, some branches are more efficient than others. And also some branches in different regions require more money. And sometimes it's dependent on demand. We're not getting into that type of problem. But the higher the demand, the more it's going to cost because you need more people. But what happens is the cost per check will go down because you become more efficient if your process is efficient. Anyway, that's a different problem. So here we have bank assignment. So how do we solve this? It's just like a transportation problem. How many of these do we ship? So here's our capacity. Here's our demand. We have to meet the demand. The payroll has to be shipped to sites 1, 2, 3, 4, and 5. These cannot exceed the capacity. It has to meet the demand and minimize the cost. Okay? So let's do it. Well, let's take these, Control C, and let's come to Excel again. Open a new spreadsheet and come down here a ways. And let's Control V and paste that in. There we go. And notice these up here are sites 1, 2, 3, 4. Let me just say 1, 2, 3, 4, 5. And this is demand. Demand. Okay. And over here on the left-hand side is personal, PER, payroll, DRAFT, draft, and government, GOV. Okay. And so that's good enough. There we go. Let's make that big. And there we are. So that's pulling everything in. And now notice this is our capacity. And up here, this is our demand. Okay, and let's center this. Arial. And center it. Okay, here we go. Now notice that in the lecture, capacity, CAP. There we go. The capacity is over here, demand's down here. So we don't get confused, let's take this, Control C, and let's transform it. Right click, and transform it. Control C, right click, and put the values in, just to be safe. So now this is the format we're used to. Okay, you might say, okay, well, that's kind of confusing. Well, you're putting it in a form that you're used to. You're setting it up so you're not going to make a mistake on the format. Okay, let's box this. Let's box this. Let's box this. Oops, it's already boxed. I didn't want it to be boxed. I wanted to blank it. There we go. Now let's box all of these. Bingo. Box these. Box these again to keep it straightforward so we know. Okay. Now down here, we're going to take these, Control C, and put them right here. We're going to take these, Control C, and put them right here. Okay. Now we'll box these in here. These are going to be our decision variables, just like a transportation problem. And we're shipping from the sites. We're matching them up. We're putting numbers from the checks to a site. These are the sites over here. The capacity, instead of capacity, let's say this is what is received. And then down here, the demand, this is what is processed. Or this is what is sent. Okay. Let's see, what did I say here? I just said totals. I guess we could just say total. And then up here, total. But if you get the idea, I hope. Okay. Now, remember to set this up. We have to sum every row, 1, 2, 3, 4, and bring this down. Sum every column, and then bring it over. Okay, and this is how you set this up. And this would be the cost here. And here I'm going to box this in. And again, I think I like the orange, because that's going to be, here's my, maybe that's a little too drastic. How about green? Because we're talking about money, aren't we? Okay, this is going to be the sum product of the coefficients per check, comma, time how many checks you're shipping, how many checks are that are being processed. So there's the cost. And so when we solve this thing, we go to data, go to solver. This is our objective function, and we want to minimize the cost by changing all of these cells. All of those cells are decision variables. Adding a constraint, well, first of all, everything for the site must be less than or equal to the capacity of the site because you can't exceed its capacity. Add all the checks that are being processed that it has to equal to, okay, it has to equal to, I'll say equal to, let me say greater than or equal to the required demand, because you might be able to process more than that, and sometimes, well, let me just say equal to. Okay, and then make sure these are right here. Okay, and then okay, where am I here? Let's just zero these out here. Delete. Delete. Okay. I forgot where it was. Okay, it's these down here. It's going to be these down here. They're going to be equal to the demand. You want to make sure you meet the demand. And I guess technically, mathematically, you could go over. You meet the demand. You can't go over the capacity, but you can process more than what the checks are. But that's all you're going to process. Let's just say equal to your demand here. Okay. And then I say, okay. Non-negativity, simplex algorithm here. I say solve, and it's going to give me my total cost, and there's going to be my schedule. I'll let you do that. But then we go on. From concern about a site processing a large number of one type of check, and if you solve this thing, a few of these sites process a large number of checks. Wait a minute, you don't want to go crazy. A limit of 230 transactions per check, per type of check for each site is being considered across the board. Now, in practice, usually there's going to be a limit on each site, but let's just keep it simple and say 230 for each type of check for each site is being considered. What's the minimum increase in cost due to this added constraint? Increase in cost. Minimum increase, so we want to add this constraint of 230 and find the minimum cost and see what the difference is between the optimal and the optimal with this added constraint. Well, naturally, if you put another constraint on it, it's not going to get any less because you're already at the minimum. If you put another constraint on it, it's going to go up. How much more is it going to go up? Is it going to be $12 or $21 or $51, $125, or even more than that? Okay. So let's bring back the Excel. So we come back to solver. And so how do we do that? Well, it's pretty straightforward. We add another constraint. And this constraint simply is, I want all of my decision variables to be greater than or equal to, what was it, 230? 230. Okay. Close this out. I'm pretty sure it was 230. Yes, 230. And then solve it again. And then when you solve it again, you'll see what the value is. You get the value from before, you get this value, what's the difference, how much more is it going to cost you to have that requirement. And so if it costs you, and notice what the numbers are, actually as it turns out, it's pretty small. It's not that much of a difference. But think about it. If you're talking about 5 different sites and you're talking about, what is this, 1,300, or now let's say, 1,400 checks and a very small amount by spreading it out more, you're going to create efficiency. You're going to improve morale. You're not dumping on one part of your process and then other people have a light. You're going to spread it out, and people are going to be more people are going to be much more amenable to that. Okay, let's see. What did I do here? I see what you're saying here, Craig. Wouldn't that be less than or equal? Let's see here. Solve. So this one right here. Oh, well, the idea here, if I add up my capacity here, oh, I see what you're saying. Then down here, if I add up my demand, is this. Okay, notice I have 100 more than I need. So I'm going to meet these exactly. And if the limit is no, I see what you're saying, the 230. Not necessarily. I want it to be, let's back up. Let me see what it's a limit of 230 transactions per check. Oh, man, you're right. It's going to be change less than or equal to 230. So a limit is the maximum. Yep. And solve that, then it'll give it to you. If it was greater than that, then it'll force 230 or more to everyone. So that's not right. You're right, Craig. That doesn't feel right, and that's not right. It's less than or equal to 230. Very good. So that's the solution there. Oops. Say okay, and then solve it. Yep, that's how you do it. You're right. And that'll give the answer. Okay, but I think there's one more. Oh yeah, after the transaction limit was implemented for each type of check for each site, the demand for payroll checks was increased to 900. Payroll. Whoa, 400 to 900, which increased the total demand for all the checks beyond the total capacity. What's the minimum cost to processing as many checks as possible with the available capacity? Okay. Payroll goes up to 900. Let's bring back Excel. Let me copy this over so I don't lose what I have. There we go. So now I'm saying payroll jumps to 900. Okay, when this jumps to 900, let me bold that, box it in. Now my demand is 1900, but my capacity here is only 1500. I don't have enough capacity to satisfy the 1900 demand. So if I solve this thing and this is equal to my demand, it's going to be infeasible. You can't do it. I don't have enough capacity to actually achieve that. But notice what the question says. The question says, what is the minimum cost of processing as many checks as possible with the available capacity? Again, this is a very common problem. What the issue here is saying, okay, do this much work, you have this much ability, this much capacity. I can't do everything. Well, do what you can. Okay, I can do part of it. I'll do what I can, and I'll say, here's what I have to give a rain check on. Here's what I have to have a back order on. I can do this later. I can't do it now. I don't have enough resources. So how would you do that? Well, here's how you do it. In order for LP to solve this thing, you come here, you add control plus, you add another row, and this is going to be a dummy row. Okay, a dummy here, and the cost is 0 because it doesn't matter. But I want these two to be equal, so therefore, exactly, sounds like most sounds like the IRS and refund checks. Yeah, sounds like most companies, doesn't it? Anyway, they just want more out of you than you can give. But I want the capacity here to be the difference. What's the difference here? 400. I want to make that 400. But now if this is 400, let me bold that and put that in. So now this right here, this sum, if I add all of this up, and this sum, if I add all of this up, and this is carried over, whoops. Now they're equal. Now they're equal. Okay, so now I do have, now that's going to be equal. But if I put it up here, I also have to put it down here. So I'm modifying the problem, put a dummy down here, and someone pointed out that, oh, you know, I said dummy. I guess I could have said Roger. But anyway, you say, oh, that's being mean to Roger. No, it's not, because this Roger is a real person. Anyway, not to be named. Anyway, and then I have to change. Solver. Okay, let me just reset everything. Okay, close. And now I have to copy this down all the way down to here. I have to change this, right, to sum all of these down to here. And then I have to copy this over, bing, bing, bing. And now this, again, has to be all of these, including the dummy, comma, all of these, including the dummy. Now I can solve it. Solver. Now my objective function is going to be that. I want to minimize. By changing variables, it's going to be all of these. There they are. Subject to the constraints. Now notice in this example here, these are equal. My capacity, my demand are equal. So I can get away with saying, okay, I want all of these to equal these. Add, I want all of these to equal all of these. So I can get away with that. And then say, okay. Non-negativity simplex. Now, if they weren't the same, then this would be less than, this would be less than that, this would be greater than or equal to that. Because I may or may not do that. And when you start adding constraints to it, we're not adding constraints, but when this constraint sets start to grow, sometimes you'll ship more than what the demand is, that kind of thing. Okay, and Walmart does that all the time. Okay, because it minimizes their logistic costs. So now I say solve, and I got it. I'll let you do that. That's how you set it up. Let me close. So now let's go back. Are we done? I don't think so. What is the total? Oh, wait a minute. The transaction limit was implemented. I didn't put that in. So let's come back and make sure that we add the transaction limit. So add, but then the dummy is not required to have a transaction limit. So I want all of these have a transaction limit less than or equal to 230. And then OK. And then solve, and that'll solve it. Now, when you get a solution here, this dummy here doesn't exist. So these are the checks that cannot be delivered. These are the sites that you can spread it over, but this is how many of these 4 that cannot be delivered. And so this is what you can deliver to minimize your cost of the available capacity that you have. Okay, good problem, and it's a very, very common problem. Okay. Then the logistics problem. Now this one is a true logistics problem. I wanted to go ahead and put a logistics problem in because logistics and supply chain management and logistics today is pretty prevalent in everything we do. An international distribution company of containers with corporate offices in Manila has been expanding operations that service customers between the Asian continent and the North American continent over the past years. Leanne Abel, VP of Logistics, has called a planning meeting to discuss possible modifications to shipping schedules because of recent changes in operations. The initial motivation for the meeting is increases in the unit shipping cost due to a series of monetary adjustments within different countries. Okay, and these costs have changed. I keep it simple here. The unit cost of shipping from each source warehouse to each destination site, capacity is in thousands of the warehouses, and the demand in thousands of the destination sites are given the table. So these are in thousands and these are in thousands, so we're talking about a lot. And these are the cost. I'm keeping it simple, real simple here. So the idea here is, again, do these costs change? They change all the time. And so how do you adjust your shipping schedule to accommodate this? Before the meeting, Leanne sent the information to you and asks you to bring an optimal shipping plan to the meeting and be ready to respond to inquiries during the meeting. What is the total optimal shipping cost? Okay, that's just a transportation problem, straightforward, no problem. Okay, and I won't solve it. I think you solve it the very same way as we did before. And during the meeting, a subcommittee assigned to review any changes in the warehouse's capacity reported that Vancouver just increased its capacity by 10%. Oh, Vancouver. It's 700. They just increased it by 10%. Okay, now they've increased that to 770. So if you change that to 770, what's going to change? Well, they added, that should not be a problem since we will have more capacity than before, so our shipping plan and shipping cost should not be affected. That sounds logical, but if you've ever done this before, the more capacity you have, and we saw that last week, it does change your product mix. It does change your mix, your transportation mix. Leanne counters, not necessarily. Increased capacity could change shipping schedules, which may lower costs, but we need to make sure. Leanne turns to you and asks you to determine if there will be a decrease in total cost when the demand for Vancouver is increased by 10%. What is a decrease in the total cost of the optimal shipping plan after the 10% increase in Vancouver's capacity? In other words, before and after. And so you're changing this to 770, you solve it again, and take the difference. That's all you're doing. I'll set this up in just a second before we go on. Toward the end of the meeting, well, let me do that now before I get to 18. So let's take these, bing, 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 Control C, bring Excel back in, new spreadsheet, come down here a ways and say, put it in there, and there it is. Okay, I'm going to take this right here and put it down here. Take these over here and put them right here. And this right here then, whoops. Okay, I don't like this at all. Sorry about this. Okay, let's I'm going to do something different here. Let's take these numbers. Oh, we don't want this in here. That's what messed me up. Let's take these numbers, bring Excel back, open this up, come down, and put just the numbers in. Okay. And then let's put LA, Vancouver, and then we have Tokyo, Shanghai, and Hong Kong. Very good. And so we're just going to solve this again. So let's bring these down. Oh, let's center, Arial. Okay, we'll take these down here. LA and Vancouver over here. Again, we'll set this up. We'll sum these. And we'll sum these. And then we get the total cost. And we'll leave the monetary values in there, I guess, and put these in there. And there they go. So if I make 1, 1, 1, 1, you can see them increasing. Okay. Then we solve it just like before, where the data solver objective function is this. We want to minimize our cost by changing these variables and add our constraint set where these are less than or equal to the capacity. We're going to add these, are greater than or equal to be safe, the demand. And then OK, non-negativity, simplex algorithm, and then solve. And that'll give us the answer to the problem. And then for the 10%, then all we have to do then is just take this. We could copy this over to the next sheet and then change this to 770. And then solve it again. And take the differences in the costs here and take the difference and see what the difference is. Okay, now 18. Toward the end of the meeting, Leanne addressed the group. Recently, I was asked by Tokyo if they would receive if they could receive all their shipments from Vancouver. About the same time, Shanghai asked if all their shipments could come from Los Angeles. Initially, I indicated that it would be too difficult for us to accommodate these types of special requests, thinking that it would be too costly. But now, since Vancouver has increased its capacity by 10%, the increase in cost may not be that great. Leanne then turned to you and asked, compared to our optimal shipping plan based on the 10% increase in Vancouver's capacity, what would be the minimum increase in cost of the shipping plan that satisfies the Tokyo, Shanghai, and Hong Kong demands of Tokyo, Shanghai, and Hong Kong and accommodates the request of Tokyo and Shanghai? In other words, if we did that, how much more would it cost us? Okay. Well, let's bring Excel back, and let's copy this over again. Okay. And now this time it's a little different. We want, let's see here, we want Tokyo, all their shipment from Vancouver. Okay, so let's just bring this up. Tokyo from Vancouver, right here. So Tokyo wants 480, they want 480 right there. Shanghai from LA, they want 440 there. So everything that Tokyo needs, they want it to come from Vancouver, so they want that 480 to be there. Everything that Shanghai needs, it's coming from LA, they want 440 there. Okay? Now, what is remaining? Well, very simply, we have 900 minus the 440 and 770 minus the 480. So that's how much we have left. Now Hong Kong needs 520. So where's it coming from? Well, it's going to come from either LA or Vancouver. We have only one destination with two sources. Okay, where are we going to ship from? We're going to ship from the one with the lowest cost. Well, 39. So it's going to come from here. But there's 520. We only have 290. So we're going to ship 290, right? But then So that's all we have left. We don't have enough to ship 520. Where's the rest coming from? It's coming from LA. So this is going to be 520 minus the 290. Minus the 290, okay? And so we're going to ship 230, and that's going to be the 520. And what's remaining is, again, 230. And we're good. And so the question is, and then I think we've already, so this is how much it's going to cost. So it's already there. You compare that with the minimum shipping cost and see how much more it's going to cost. Sometimes it doesn't cost that much more because a lot of times they're very close to optimality. It's not going to be optimal because we're taking 36, which is the minimum, but 40 is more than 37 here. But then this is a minimum here. And so it's going to be a little bit more. How much more? I'll let you figure that out. Okay. Now 19 and 20. On this one, this is going to be pretty much like the memo. A small company manufactures 3 sizes of their picture frames that require the processes of carpentry, finishing, assembly, and packaging. Each process resides in a department that works on an 8-hour works on 8-hour shifts. The production standard in each department is reported to be the number of products produced during a fixed production time, like 8 hours or 4 hours or 16 hours. The production standard in the carpentry, and then right here, let me just do this. The production standard in carpentry department is reported to blah, 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 blah. The production standard in the finishing department is reported to blah, 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 blah. In the assembly is reported to blah, blah, blah. And the packaging is reported. And finally, the profits are that. Okay, this is carpentry. This is finishing. This is assembly. To keep these straight, and this is packaging. And this is the profits for each of the frames. Small, medium, and large. And there they are. Now, each frame has a minimum production requirement, of 6. Minimum production requirement, let me bold that. So there's the set. And notice I'm not setting it up in a matrix. I'm giving it to you in a sentence. So you create the matrix, and then you solve it. Okay, so let's do that. Now, in order to do that, we have to set up the actual production standards. But notice the production standards on how they've done it. The production standards are given by how many can be produced in a certain amount of time, right? And so let's do this here. We're going to have 20 small frames in 2 hours. The carpentry, 20 small frames in 2 hours. Okay, so we have, let's do it this way, is reported to, okay, small. 20 small frames in 2 hours. So how many hours per frame? Okay, it's 20, it's 10 20 small frames per hour, but within the matrix of a product mix problem, you want the number of hours per frame. Okay, so this is going to be 2 divided by 20. That's your production standard. That's how many hours per frame. Now for a medium, it's going to be 4 hours for 32 frames, and that's hours per frame. That's your production standard in your matrix. And then for large, it's going to be, what do we have? 2 hours for 12 hours per frame. And so those are the numbers that are going into the actual matrix. Okay, so I'm not going to that's the key here. And the reason I did it this way is this is pretty much how the memo is going to be, the memo 2 is going to be presented. And so what's key is putting together the production standards using this concept. The reason I do this is because a lot of times this is exactly how production standards are generated. Well, the last 8-hour production, we made 200. So there it is. It's an average of 200 per 8-hour production. Oh, okay. So you don't put 200 per 8 hours. It's 8 hours per 200. That's hours per frame if you're trying for product. So you got to be careful when it's given to you how you transform that into the numbers you need. And then down here are the actual profits. And then we have a minimum of $6 for each one. I mean, 6 units for each the small, medium, and large range. So none of them can go to 0. 6 is the minimum. What would be the profit from producing 1 dozen of each for one shift? Now that we're talking about one shift at a time. So you just say 12, 12, 12, and see what the profit is. So here, I put this to get the optimum. I put this to have an even dozen. And so this is done to optimize one production shift. A lot of times this is done to say we have a dozen every shift, and then you can control the demand, the resource supply chain, and the demand customer chain, customer relationship management. You can control the upstream and downstream supply chain around a fixed production level, and so it's very constant. And you can plan upstream and downstream. And if it's all part of a LP, then everything can be controlled, but you're changing things around, and sometimes it's confusing for the people who are driving and the people who are doing this stuff. But anyway, 2 different problems to solve it. The key is this right here initially. The rest of them is just like we did before. Hopefully no questions. We have a couple weeks to do this, so you can always ask questions about it down the road. Okay, that's a homework. The third thing we're going to cover today is the memo. So let's bring up the memo. And again, if you have any questions, I can go back to the quiz or the homework. We have what is this? 6:30, 7:30, 8:39. We have 30 minutes left. Should be 2.5 hours is one of these lectures. Okay, let's bring up the memo. There we go. Memo 1. Now, this memo 1, I start just to make sure people remember how to do this. I follow the instructions from the syllabus. I copy them here just to refresh people's memories. Okay, and this is the format because a lot of times people don't do the format initially. And then you have a video here. Okay, so let's come in here and look at the assignment memo number 1. So let's go through this. Allison and Andrew Anderson have successfully operated Speedy Pizza in a popular ski area in Colorado. Although they believe sales have been increasing for both dine-in and carry-out, the carry-out business seems to be presenting problems. Okay, let me just highlight as I go through. They believe sales have been increasing. Let me bold that. Okay. They have asked us for a monthly forecast. Okay, let me bold that. They have asked us for a monthly forecast of the carry-out pizza for the next fiscal year, along with some insights of the nature of the demand for their carry-out pizza beyond next fiscal year that would help them with their planning. So the key on these memos in communications is unfortunately, many times students will solve the problem that there's the answer. But that's not what they asked for. They ask for something very specific. Make sure that your client, your customer, your company, what they want you to do, you provide that. You can go beyond sometimes, and that's fine. But if you don't give them what they ask for, it doesn't matter what you say, you didn't deliver what was requested. So they request a monthly forecast. So I want 12 numbers for 2021, a monthly forecast. And insights, I'm looking for insights of the nature of the demand that would help them in the future. So those are the two things that are deliverables. 12 numbers, that's a monthly demand, and then insights for the future. Here's what you need to know. For example, sales have been increasing and seem to be presenting problems. I'll go ahead and darken that. Why? Is it increasing? Why do you have problems? What does that mean? I gladly agreed, knowing that my associates could do it and do both requests well. What both requests? The monthly forecast and insights. Okay, they gave us, the Andersons have indicated to me that the demand for dine-in slightly fluctuates throughout the year, but seems to be quite predictable. Dine-in. However, the demand for carry-out seems to be highly volatile all year. This has caused them supply problems since they plan for deliveries in advance because of their mountain location. They've provided us with the following carry-out pizza for the last 4 years. We have plenty of data here for the last 4 years. Analyze the Andersons' problem and requests. Prepare a response memo to them adequately and appropriately responding to the request. Prepare a separate technical memo to me, presenting the details of your approach and analysis. Prepare a video presentation to the Andersons, presenting their requested forecasts and providing insights that would help them in their future planning. So there's 3 things going on right here. A response memo to them, a technical memo to me. In other words, you're telling me how you solved it. And then finally, a video presentation to the Andersons. So the audience is important. Now, the reason the audience is important is because if you're responding to them, you're going to tell them, here are the forecasts, and here's the insights in a 1-page memo. And in that 1-page memo, you're saying, here are the forecasts, here are the insights you need to know. You're not telling them how you solve the problem. They're not asking for that. They don't care how you solve the problem. They want the results on how they're going to use it moving forward. Now, to me, the technical memo, there's where you tell me how you solve the problem. I made this a while back. I made these numbers a long time ago. A good point. Shocking, their carryout went way up in 2020. I made this a while back. As it turns out, carryout in 2020, I think carryout in 2021 is going to be even higher. So it has been increasing over the years to them, but it's kind of like, hey, yeah, it did increase in 2020. Good point. Okay, so before I go on, and also the video is to the Andersons. Now this is a response, is a presentation in written form with graphs, tables, whatever I want to do. I don't want to tell you how to do it. You think the best way for you to present it. Each person is a little bit different. Now the video presentation, that's different. Then it's visual and you're talking. And so the visual then, the graphs will carry much more of the weight, not so much the the talking and the audio. So make sure the presentation is very clear what those forecasts are, and then the insights are very clear on how they move forward. And so presenting these 2 things in a memo is written form, and they can analyze it. You can have more detail. Presenting it in a video, the detail will be confusing. It has to be very clear and presented, and the results have to be very clear in the presentation. Before I leave, let's actually work this thing. I want to work it for you. And I apologize if you wanted to work it yourself. Maybe you already did, but let me work it for you. Becca, should we include charge graphs in the written memos? You just answered that. Thank you. Actually, I want to emphasize it. I'm glad you asked it again. I want some people. Very good point. I want to answer it again. Some people put graphs and tables. Some people don't put any. They'll just have a sentence, and everything is there. It's just a storyline. Oh, if you do this, you're going to get this number for January, this number, and they put it all in a paragraph. Fine with me. All the information is there. There's a big world out there. People look at things differently. They do things differently. They think differently, and we don't know the Andersons. And so, whatever you feel comfortable in presenting, do it your way. Because I want to see all different memos coming through, as long as all the information is there and it's correct. So what I'm looking for in grading is the information there? Is it correct? Did you say anything wrong? So if you're not sure, don't say it. Okay, so let's open this up. Let's come down here. Let me Control-C this thing. Yep, there it is. Okay, now to be careful here, let me take these numbers. I don't like the two things here. Down here, and let me paste the values. Let me take these right here and paste these values right here. And then take the months here and paste them here. There we go. And let's home, Arial, center. Very good. See, this is cleaned up. This is much better. Oh, maybe not. Let's bring these out. Let's align these. There we go. And then actually let's bring these over here. Let's bring these over here. There we go. And then let's format. And then let's take these here. Let's zero this out. And then let's broaden this out a little bit more. It's sitting at probably 9. It's going to be better. Okay, there we go. Well, still I don't have it. Okay. Okay, now first of all, remember what I said is make sure, Becca, should the presentation include how we did the analysis or just the results? Note it, remember, the presentation is to the Andersons. So you don't need to say how you did it. Although, if the Andersons are very quantitative, if they're engineers, they would love to see that. And that might help them in their insights. But make sure you give them the forecast. Dana, are you expecting vocal audio over PowerPoint slides or a video showing our faces of us explaining? However you want to do it. Some people have their like I do, like you can see me in the corner. Some people do that. Some people just have the vocal. However you want to do it. I'm not too, however you want to do it, that's all I want to see. And I'll show you how to set up the PowerPoint here in just a second. Okay, but what we have here is the data. Let's work this real quick. Okay, and again, the purpose of the memo is a communication. And if you're going to communicate things in a business, it's a team. I feel we're a team. I'm part of the team. This is what I did. You can use this as much or little as this as you want. First of all, let's plot this. Let's take this. Let's come over here and let's plot it. There we go. And you know, if we plot this with a stacked plot, here's the years 27, 18, 19, 20. We can see there's a pattern every year, right? Aha. And every year it's going up. So there's a trend here, and also there's seasonal component. Now, some people might want to say, you know, I would much rather have a line plot to show that. So let's take this, Control-C that baby, come down here, and Control-V and paste the numbers again. And so right here, let's take this matrix and put it into a line vector, a column vector. Equals this. Make sure I do this right. Be very careful. Ka-ching, ka-ching. That's 8139, yes. And this is going to equal January up here, yes. And now, let's take this. If we see what I did, in other words, I want to take this, 2018, this 4109 is going to be here. After 2018, the next day is 61, 15 is 2019. After this is done, then it's 8139-2020. So I do this and I copy it all down, and you go all the way down. Whoa, there we go. Little, whoa. Copy it down, and then it stops at 0. What does it stop? Oh, wow, I went way far. There it is. Alt-ED, ed, will erase everything. And this right here represents my column vector. Highlight that, Control, Shift, down arrow, Control C, copy this thing, come over here, and let's just put this right here and paste the values. And there it is. And now, I can, and this is my time series. Okay, and now I can take this, in other words, Control, Shift, down arrow, insert, and let me do the chart again. Let me see if it's going to, oh yeah, there it is. So boom, there it is. And now I have a line plot. So there I have a stack plot. I have a line plot. You can change this around and format this the way you want to. You can change the colors. You can change the markers here. I think we did that before. If not, I'll show you how to do it in the office hours. But now that we're here, we say, okay, now we see. You plot the data. We plot it 2 different ways. Here's a stack plot. Here's a line plot. And so some of you might say, well, this is, I can see that I have the trend here and the pattern is repeating. Some of you may want to use this. Some of you may want to use both. Some of you may want to use neither. Okay? But whatever you use, you want to say that we have a trend and we have a seasonal component. Well, if you have a seasonal component, let's move this out of the way. Then what do we want to do here? We want the trend, right? And let me change this up here to 1, 2, 3, 4, just to keep it simple. Equals slope. The y's are going to be this, comma, and just say 1, 2, 3, 4 for the years. F4, return, copy down, and there it is. There's our slope. Okay, and notice, you're right, Craig, look how it just keeps, look how it increases. And this slope is, well, we can tell it's going up. Okay, and the differences here is due to seasonality. Let's take the average. Take the average of all the trends, and that's a seasonally adjusted trend, and it's going to be that. Actually, going to see seasonally adjusted trend. There we go. And if I take the seasonal indexes, I can take this divided by the seasonally adjusted, F4, and then copy that down, and there's my indexes. You can use those if you want to. Now, I'm not telling you what to use. I'm saying it's here if you want to use it. It's here if you want to use it. You can see how to generate them. And then you have your forecast. Okay? And the forecast for 5, 6, 7, 8, we can do this all kind of cool ways, equals the intercept of the Januaries, comma, 1, 2, 3, 4, F4, plus the slope, or the trend, it's going to be that, times 5. Okay, and I can copy this down. The 5 here, let me just put a 5 in there. Now it'll work. Now, when you do this, I want to caution you, be very, very careful in looking at this because when you're reporting this and you're presenting this, then you want to be very, very careful in like 10,000 right here, 10,156.5 pizzas. Well, that's your forecast. Well, it is very distracting, and in some environments, some situations, they'll look at that 0.5 and they'll be insulted. Like, why am I looking at point? They'll even look at 6, and round that to 60, okay? In other words, if you're forecasting a month making 10,156 pizzas, does that 0.5 have any meaning? No. And I've been in meetings, meetings, where people will look at this and they will say, why are you showing that? You obviously don't know what we're trying to do here. You're giving us things that we don't need. And they will focus on things. Don't give anyone anything that they can argue. Okay, and I would just bring it down to units or even round it. Okay, and I even bring the trend down. Now, when you present this, you present it this way, but I'm using all significant figures. Never round during calculations, only round presentations. The indexes, I don't know, we can bring down to 4 places, 3 places maybe 2 places. Doesn't matter. Okay, but once we have this, I can also do it for 6, 7, 8, etc., 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 if I wanted to. Okay, so there's our forecasts. So these are the kind of numbers that you would put in there. And if you want to put this into an Excel file, I've already mentioned this before. Up here, you can copy as a picture, as shown when printed, say OK. And if you do the clipboard, there is the graph. There it is. So what are you doing here? What you can do, if you have a Word file, and here's a Word file. If I have a Word file, I can go to my clipboard and say, ready, go. And then I can format, I can reduce that. And we did this before. And then you can start moving this around if you want. Okay. Now to click this, move with text, and you can move it around into the text anywhere you want. But then if you open PowerPoint, okay, let's bring up this PowerPoint. Let's take this out here. Whoops. Let's do the PowerPoint. Let me get out of this. Okay. Yeah. Let me open a PowerPoint. There we go. Let me open this PowerPoint. And so what you can do here is have a blank PowerPoint. Up here on the design, you can design it any way you want. People will design it different ways. You can have this, you can have this, you can have this. You can go crazy if you want, or just have nothing. Just have a white theme. Okay. And you can take this out. You can take this out. They're trying to help you out here. Over here, right click, and then you can duplicate the side. Right click, you can have a new slide. Right click, you can delete slides. You can right click, shift. You can then shift. You'll highlight both slides. Then you can duplicate. Both those slides will be duplicated. The point is, and then you come up to Home, your clipboard, and there's your graph again. You can come over here, post your graph, and you have your graph in there. And then if you want to have texts, the way I do the text up here is I'll come up here and insert another table right there. And I can format the table. With a table, the shading is going to be no shading. And so I can type in there. Speedy Pizza. And then make the, it's white, so let's make the font black. Make the font black. And there it is. And then I can format this and make it big. And so I'm not really too concerned about how professional this is. I just want you to make a video. But then once you create your PowerPoint slide, how do you make a video? Okay, let's bring this back down and come up here, slideshow. When you do a slideshow from the beginning, okay, or over here you can say record your slideshow. You need a mic with your laptop, or I have a blue mic here, but you need a mic. So record your slideshow, and you can record from the current slide or record from the beginning. Let me record from the beginning. Ready? Go. And so it's going to start recording over here. And so you can say, okay, ready, record. 3, 2, 1. Let me get out of this. Let's do this again. Record from the beginning. See if I can bring this over. There we go. And so you're going to record from the beginning. Record. 3, 2, 1, 0. And then you'll start talking. You have to wait a little bit. Say, this is diagram number 1. And this is going to be the speedy pizza. And here is a line graph. And the next one is going to be a stacked graph. And here the forecast. Here are the insights. And then stop. Okay. And then once you have that, and then you can download that from the presentation. And then you will have, you can download that from your presentation. And then you will have, well, when you download it, you can either download it as a PowerPoint presentation, but then you can save it as an MP4. Okay, in other words, you will have audio in your PowerPoint then, and then you can save this as an MP4. Stop, clear, settings, camera, notes. Okay. And so if you have any questions on this, I'll be more than happy to help you. This is probably the easiest way to do it. Now, some of you have probably done it other ways, which is perfectly fine. And if you did, then that's great, however you want to do it. But give it a shot. And if you've never done it before, now it's time to learn, because I'll help you on generating these things and setting these things up. And after you set them up, you'll have a product. And you'll have 4 of these things. And again, it could be just one panel. It could be 2 or 3 panels, however you want to do it. Okay, it can be in detail, it can be not in detail, etc. Okay, so that's all I have for this quiz 2, homework 2, memo 2. So let's see, I got so many things open. Let's start closing some of these things out, minimizing anyway, to see where I'm at and what I'm doing here. Okay, that's all I have for now. I hope this helps. And between now and the next time I see you, I have office hours on Omar. The technical memo. The technical memo is not. Remember the PowerPoint. The PowerPoint video is just for the Andersons. The technical memo is just for me, and that's just a Word file. So there's only one page for a response memo to the Andersons, 1 page technical memo to me, and then a presentation, a video to the Andersons. So those are the guidelines, okay? And so however you want to do that, whatever you want to put in there. So between now and the next time I see you, if you have any questions, I'll see you during office hours. Friday night at 7, Wednesday and Friday at 7 p.m. office hours, and I'll help you as much as I can. You can share your screen and I'll walk you through things. So you can get the first one done for Sunday. So that's all I have for tonight. Again, I want to appreciate all the questions. I hope this has been helpful on how to work the problems and then how to start putting together a PowerPoint and a video. And I might want to say that the memos and the videos I feel are important deliverables from this course, and I want everyone to do them. And if for some reason you do it and it's not right and it doesn't have audio, or you've made a mistake and you want to make it better, you can do it better. And I will change the grade on that memo thing, okay? And so I will help you, even if you don't get it done, but you want to keep doing it to try to get the memo done. Okay, I don't want you to put it off to the end, but I will help you, and the deliverable. That's why the deliverable or the submission of the memos are different, because I want to make sure you get those memos done, because I think that's a really good positive takeaway from this course, to have 4 good memos leaving here, because these memos have a good spread of the kind of problems you'll be dealing with in business, you'll be solving in business, and the types of problems, let's go here, and the kind of problems that you'll need to know about and communicate. And so hopefully everyone will be able to get all 4 of those memos done. And so the due date is strict only in that I want you to do the due date. If you go past it, I still want you to do it by the end of the course. Okay, that's all I have for tonight. So between now and the next time I see you, I want to urge everyone in these times to be safe. Don't take anything for granted. Take care of yourself, okay? Take care.